10.4, inverse of a function. Okay, so let's talk about what a relation is first. A relation is just a group of points. So in this example, here's a group of xy pairs. That's a relation. Here's another relation. It's just written as an xy table this time. Okay, so if you've got a relation and you want to find points that are on its inverse, what you can do is switch the xy pairs. So if a relation contains the point AB, then its inverse is going to contain the point BA. So all you have to do is reverse the xy pair, and then this would be a point on its inverse. Okay. So when I'm looking for points that would be on the inverse of this relation, I'm just going to switch these xy pairs. So -4, -3 would be on it. 0, -2. I'm not changing any signs. I'm just flipping the xy pairs, swapping the x and the y for each one. Okay, and yeah, I'll do the, I'm not going to read them all out, but I'm just switching those pairs. And this is the inverse of that relation right above it. Okay? And you can do the same thing with an xy table. All you need to do is flip it upside down. So I'm going to now make the y's that were on the bottom, the 4, 5, 6, 7, 8, will be my x's. 4, 5, 6, 7, 8. And the x's used to start with -2. Now the y's will start with -2 and count up to 2 there. Okay, so I just switched that xy table, and then there's the inverse. Okay, so it's fairly straightforward when you've got just a group of points written. It's a little bit more difficult when you've got an equation written, because this is really a big group of xy pairs, all of the x's and y's that will satisfy this equation. Okay, so if we want to find the inverse of this, we're going to have to write a new equation. And we're going to use the same basic principle. We're switching the x's and y's up here. So what we want to do first is write this with a y instead of f of x if it's written in function notation. So I'm just going to write it like that. Okay, and then I'm going to switch the x and the y. So I wrote it with a y. Now I'm going to switch the x and y. I'm just going to switch where they are. Okay, and the last step would be to solve this for y. This is actually the inverse, but I want to rewrite it so that it's in y equals form. Okay, so last step, solve for y. So I'm going to subtract 2 from both sides. Now I've got x minus 2 equals 3y. And then I'll divide the whole equation by 3. Okay, and you could divide the x by 3 and divide the -2 by 3, or you could just divide them both by 3. It doesn't really matter. It's going to be equivalent. Okay, so now I've got just the y over there and x minus 2 all over 3. Okay, and you can flip this equation around. It doesn't matter. You could put the y on the left if you wanted to. You could also split those fractions into 2 separate fractions, x over 3 minus 2 over 3. And you could also put it back in function notation, but I'm just going to leave it like that for now. Okay, so let's try it again on this one. I'm going to just write this with a y first. Then I'll switch the x and the y, and you could do those first 2 steps all at once if you wanted to. I'm just trying to be clear. And now I'm solving for y, so I'm going to start by adding 4 to both sides. And then I'll divide by 5. Divide the whole equation by 5. Okay, so now I've got x plus 4 all over 5 is going to equal y. I'll just flip that around like so. There's the inverse. Okay, let's try a couple more. Okay, so let's see. I'm just going to switch the x and the y all at once. I'm just thinking of the f of x as a y, so I'm going to put the x here and the y here. Okay, then I'll add 4 to both sides. I need to isolate y. So now I've got x plus 4 equals 1/3 y. All right, now to get rid of the 1/3, I want to multiply by 3, because 1/3 times 3 is 1, and then I'll be just left with a y there. Okay, so on the left side, I want to do 3 times everything, times that quantity x plus 4. So I'm not just multiplying the x by 3. I want to multiply the x and the 4 by 3. Okay, so that'll give me 3x plus 12 equals y. Okay, and I'll just flip this around. Okay, and there we go. There's my inverse. And let's try one more. So I'm switching the x and the y first, so that if this is the y, I'll put the x there, and I'll put the y where the x used to be. Okay, and I'll subtract 2. And now I'll multiply the whole equation by 4, because that's going to leave me with just y on that side. And I got to remember again that I'm distributing this 4 into both terms over there, multiplying everything by 4. And I'll flip it around. Okay, and there's the inverse there. Okay, on the next page, let's look at something called the vertical line test. So you might see problems where you have a graph and you're supposed to say if it's a function or not. Okay, and here's where the vertical line test is going to come in really handy, because this is going to determine if a relation is a function. Okay, and here's how it works. If any vertical line passes through the graph more than once, the relation fails the test. Okay, so looking at this first example, so a vertical line, you got to know that's a line that goes straight up and down. Okay, so if I put a vertical line, say, right here, well, then this would intersect with my curve more than once. Okay, and it says if any vertical line passes through the graph more than once, the relation fails the test. Okay, so this is going to fail the test. All right. If it passes the test, it's a function. If it fails the test, it is not a function. So my answer here is going to be no, this is not a function because it failed the vertical line test. Okay. Now on this one, anywhere that I put a vertical line, say I put one right there, it will pass through once, but that's still going to be a pass. It's just if it passes through more than once. So, you know, over here, yeah, it doesn't cross at all. It actually would way off the top of the graph, but I'm just making sure it doesn't cross more than once. So this is going to pass the test, and that means that yes, it is a function. Okay? This one, there's lots of places you could put a vertical line that would pass through more than once. You could actually get it to pass through 4 times if you put it in the exact right place. Okay, so that one is going to be a no as well. Okay. All right. So that's I use the vertical line test when I want to check if a relation is a function. Sometimes you might need to check if the inverse of a relation is a function. Okay, and that's when we're dealing with a graph again. All right. So it gets a little confusing. We have something called the horizontal line test, which is very easy to use. It's still going to be used to test if something is a function or not, but it's not testing when I'm looking at these problems. It says determine if the inverses are functions. Okay, so the horizontal line test is going to determine if the inverse of a relation is a function. Okay, if it passes the test, it is a function. And if it fails, it is not a function. But this time we're using a horizontal line. So I can see, okay, this function itself would fail the vertical line test, or this relation would fail the vertical line test. It's not a function. But if I want to check its inverse, I don't have to actually graph the inverse or figure out what the inverse is. I just do the horizontal line test. So wherever I put a horizontal line, it's not going to pass through more than once. It'll pass through once at a maximum. So this is going to pass the horizontal line test, and it means yes, the inverse of this is a function. Okay, this one's going to fail a horizontal line test, and that means the inverse is not a function. This would pass no matter where you put a horizontal line. It's not going to pass through more than once, so this is going to pass, and that means that the inverse is a function. Okay, so you just have to memorize that vertical line is for the function itself. A horizontal line test would be for the relation's inverse. Okay, I said the function itself, the relation itself. Okay. Okay, third page. we're going to be looking for inverses again, and these are quadratic equations. So they're quadratic because it's got an x squared in there on all of these, okay, on the original. Well, so this one has a square root and this one is a cube root, but these first two are quadratic equations, okay? And so the process is going to be the same. We're going to switch the x and the y, but we've got this thing which is a little confusing, and it's in both of these. But let's just talk through the first piece. So just ignore that for the moment. So I'm going to switch the x and the y. So if f of x is the y, then I'm going to put an x there. I'm going to put a y over there. Okay, so I've switched the x and the y. Now I'm going to subtract 2 from both sides to start isolating the y. So I've got x minus 2 equals y squared. Okay. And now to isolate y, I'm going to have to take the square root of both sides. Okay. Now, when you take the square of both sides of an equation, you would usually put a plus minus in front of the square root function technically, but we're not going to do that here. I'm just going to put the square root of x minus 2, and I'm going to say that that equals y. Okay. And then I'll flip this whole thing around. Okay. And this is my solution. Now, this is saying that x is greater than 0, and the reason greater or equal to 0, and the reason for that is because if we had a number less than 0, we could get a negative number under the radical. And so it's really just, it's a kind of a technicality, but it's we have this restriction on the domain. So this would be a parabola, but since x is greater than 0, it's really only, if you were to graph this, it would have a vertex at 0, 2, because it's moved up 2. But it's really only the right half of this parabola, so you wouldn't be graphing the left half, okay? So then when you take the inverse of it, you get half of a sideways parabola, okay? And that's what this thing is about, okay? So we got the same kind of deal here. You don't really have to worry about it too much. It's just, it'll be built into the problem usually, okay? So you're switching the x and the y. Again, and I'll add 4 to both sides. Okay, now don't take the square root yet because we want to divide by 5 first. So now I've got x plus 4 all over 5 equals y squared. And now I'm going to take the square root of both sides. So I'm going to get the square root of that fraction, and I'll just flip it around. Okay. With a cube root, well, I'm going to be taking the cube root at some point when I'm doing this problem, but it's okay to have a negative under a cube root because you can raise a negative number to the third power and have it come out negative, okay? But I'm going to switch the x and the y here. Okay, and that's why it doesn't have any restriction on the domain like the parts A and B do. So now I'll subtract 5 from both sides. Now I'll divide by 2, but don't take the cube root yet. We are going to do that, but not yet. Excuse the bell there. I was trying to beat it, but I didn't get there. All right. So now I'm going to take the cube root to isolate the y. Cube root of that whole fraction. And that will isolate y. And then I just flip this around and I'm done. Okay? All right. So let's try one more. So I'm switching the x and the y here. Whoops, this would become the x. Okay. Now I'm going to, this time I'll need to square the equation. I'm trying to isolate the y. So first I want to square both sides of the equation. And that will, now I'll have x squared equals y plus 2. And then I'll subtract 2 from both sides. So now x squared minus 2 is going to equal y. Okay, and I'll flip this around. Okay, now this is a little bit hard to remember, but when we started with these quadratic functions, that's when we limited the domain. Okay, so we want to do the same thing when we're ending with this, because we want to make sure that we don't have negative numbers underneath the radical. Okay, so I want to say that x has to be greater or equal to 0. X wouldn't be a negative number, so it means it'd only be the right half of this parabola. Okay. All right, that's the end of the section, and I'll see you next time.